Okay, so let me give you a quick overview of what we'll be covering in this talk. Okay. So this is about what are the key factors that we need to consider while serving LLMs or applications based on LLMs. We'll go through working on short, recap of how transformers work. Then we'll go through the hardware requirement for serving LLMs. What are the key metrics that we need to keep in mind when we are serving LLM-based apps? Then we'll be looking into hands-on code, how text is generated via LLM. Uh, then we'll be covering certain techniques that helps us generate text faster. Okay, it consists of KV caching, batching, continuous batching, quantization, and then at the end briefly we'll talk about the adapter-based fine-tuning. So yeah, let's get started. So goal is to understand what are the things that we need to keep in mind when we serve LLMs. LLMs, although we are saying LLM serving, but we will be primarily focusing on decoder-based LLMs in this talk. This is a decoder-based LLM architecture, and roughly the key things that we need to keep in mind is that token goes in from one side. Let's say that we have a text quick brown fox. It will go from here. Okay, and the output will be the next most plausible word. Okay, let's say jump. Okay, uh, then the recently generated output will go again. So quick brown fox jumped will go again, and then on will come out. So this is called auto-regressive way in which text is generated. Okay, so it's auto-regressive in nature. In this diagram, what we need to what we'll be discussing down the line is this attention. Okay, so all these tokens, let's say quick brown fox, if they are here, they are processed in parallel. Okay, that was the key selling point of transformer, that it was able to process the sequences, the tokens in parallel rather than in RNNs, going one by one. It helped us free ourselves from recurrence. Okay, that was the key selling point of transformer, which has worked for it. So all the tokens are processed in parallel, and it works in auto-regressive way. So that is something that we have to keep in mind, that will help us down the line. Now, before we talk about what are the different techniques, it's a good idea to have a rough understanding of, when we talk about LLMs, what are the hardware requirements, right? So let's say that if you're looking for, if you're reading something about, Llama 7B, 3B, 13B, right? What are the hardwares we are talking about? What are the limitations, like constraints, hardware constraints that are put on it, right? And then we can make our decision that what is the model size we want to work on. So let's say we are working on a 1B model, right? So what is 1B here? There are 1 billion parameters in that model. And if we say that they are represented in float 16, that is 16 bits per parameter, then it will take us 2 gigabytes of memory. Okay, so 1 billion parameter will take uh, twice the amount, like, which is 2 gigabytes, since we are using float 16. So to efficiently serve models, okay, we roughly use this formula that we add 0.25% to it. That's the minimum requirement, and you should be able to work on it, that model, with small batch size. Okay, as the batch size increases, you might need to just add zero point 0.5 more to it, and this is the ideal size that you will need to work on this model. Okay, so if you are working on 1B model, then the GPU memory that is required to work on it is 3 GB. Okay, if you're working on 7B, then ideal GPU requirement reaches 21 GB. Okay, and as you move forward, then it's becomes more and more difficult to work on consumer GPUs, and you might need to rent out the GPUs, okay, from different service providers. So this is how model size and GPU memory are related. With CPU memory and GPU memory, it's a good rule of thumb that take twice as much as GPU memory as. Uh, so your RAM should be CPU RAM should be twice. Why twice? Roughly when torch pickle models are loaded, then an empty object is created and then it is populated. And roughly for you to do it well, you should have twice as much as RAM to load it in your RAM, and then from RAM it is moved to GPU RAM. Okay, so this is some of the hardware considerations that you need to make uh, while choosing which model to work on. Okay. Next, we'll talk about what are the key metrics that we care about when we are doing LLM inferencing. So first thing is time to first token. So let's say that you posted a question. Okay, what is the capital of India? And that goes into the LLM. Now, what is the time that LLM took to give the first token back? Okay, that is time to first token (TTFT). Uh, when you have short TTFT, then your model appears very responsive. Okay? Your app appears very responsive. Second metric is time per output token. So when the model start generating tokens, then how much time is each token taking? Okay, to reach the user. That is something is captured in time per output token, and more less is the time per output token, uh, more fast the LLM is perceived by the user. Now, latency is something that can be thought of as sum of 1 and 2. Okay, so once the user posted a question, uh, the entire text is generated. What is the total time? Like time for first token to come plus the time taken by the remainder of the tokens to reach the user. That is latency. Uh, then we talk about throughput. Throughput is a system-wide metric, number of output tokens per second your server is producing across all users and requests. That is something captured in throughput. Now, based on your use case, you might care about different metrics. Okay, let's say you are building a chat app, then you would definitely care about latency. Okay, how fast user is getting the answer to what they are asking. Okay, if you are, let's say, setting up a batch processing system, let's say you want to generate some text based on raw PDFs or raw text, okay, in batches, uh, then you care about throughput because it is anyway a backend service. You care about how fast you can process whatever documents that you have, right? So in that case you will care more about throughput. So now let's talk about text generation, and then we'll go through the code how it can be implemented. So any text generation has two phases. One is pre-fill phase, another is generation phase. Okay. So let's say that you ask a question. Okay. Uh, how does LLM works? Right. You put it in ChatGPT. Then what happens is before any generation start, LLM has to make sense of the text or prompt you have hit. Okay, so that part goes into pre-fill phase, where model is not producing anything new; it is making sense of the existing text or prompt that is given to it. Okay, so it consists of the text is tokenized, then all those tokens, uh, key value, attention mechanism. It goes through all the layers, and then finally it comes with the token, the next token. Okay, so this is the pre-fill phase, and once the initial prompt has been generated, then initial prompt has been processed, then the generation phase start, which happens in as we discussed auto-regressive manner. Okay, output is being produced, then output becomes part of the previous input, then again given as input to LLM, and then in an auto-regressive way it produces the entire answer, and that is called the generation phase. Okay, uh, yeah, so let's look at the code. So basically here are some imports related to library we are using. We will be using Hugging Face transformers library, and for the sake of discussion, we'll be using GPT-2 model. Okay. It's a small model, and we should be able to run it on our CPU for demonstration purpose. Okay. So here, what we are doing is we are initializing the model, and we are initializing the tokenizer. From pre-trained means it's already pre-trained and on Hugging Face. Basically, this just downloads it and loads it in model as well as tokenizer. Okay. Now, what we are going to do is we are going to generate text in a sequential manner. Okay. So these are our input samples. So for the sake of simplicity, I have kept the token count same, and these are of different length. Okay. And out of these input samples, we are forming a request queue of size 12. So there will be total 12 text for which uh, generation is to happen. Okay. Uh, we have this function called generate token, which will take the current input and generate the next token. Okay. Uh, what we'll do is we'll go through. This is our generate text function, which takes the text and then generate the remainder of the text. Okay. Let me run it for you, and then we'll go through some of the points in the code. Okay. So when I run it, so basically what we have in black is the prompt that we gave, and what we have in red is the text that has been generated by the LLM. I won't call it LLM, but by the model. Okay. So total time taken by 12 example is 14 seconds. Okay. So just to go through the code, what we did was this is our pre-fill stage where we pass the text, and using tokenizer, it was converted into numeric IDs. Okay. Uh, then what we did was that we passed that input coming out of tokenizer into generate token. Okay. And it will return us the next token ID. Once we have the next token ID, what we'll do is we will gather the next input that is supposed to go to the model. Okay. So we added the recently coming output, next IDX, in the existing input. This is happening over here. And we have this thing called attention mask. So what we'll do is, since we now have one more token than the initial text, then we'll add just one to the attention mask. Okay. That's all what we'll do here. And this will generate our text in a sequential manner, auto-regressive way. And this is taking around 14 seconds. So 12 examples, they took 14 seconds. Okay. Now, this is kind of very inefficient way to generate text. Why? To discuss that, we can talk about KV caching. Okay. So let me go back to the figure here. Okay. What happens is all these tokens that initial prompt had, they are processed in parallel. Okay. And in each decoder block, attention layer, they have their KV representation. Okay. So let's say I pass quick brown fox in this, then the KV key value pairs, generated for that particular token here. Okay. For these token here, they are going to remain same throughout the auto-regressive process going on. Okay. So we don't need to calculate them again and again. So what we do is we cache the key value pairs of the tokens that we have seen so far, and then reuse them in the generation. Okay. Think of it like when we calculate Fibonacci series, right? So we already have the input values for the previous ones, right? So we don't need to calculate them again and again. So think of it like we cache those values and then reuse them. So our next example will do just that. Okay. Let me run this for you, and then we can discuss some details about it. So again, 12 examples. Okay, and this time using caching, it took 4 seconds in comparison to 14 seconds. And why this reduction in time? Because now we are not passing the input tokens again and again and calculating their key value pairs. Okay, what we are doing here is we are processing the token. We are tokenizing the prompt, initial prompt, and then at the time of regeneration, what we are doing is we have generate token with past function over here. Okay, so what generate token with past function does is it gives us the next token, and it also gives us all the key value numbers corresponding to what it has seen so far. Okay, so now for the next time we generate, we are going to use these two things. Okay, so how does that work here? Instead of passing the entire sequence we have seen so far, we just pass the recently generated next token. Okay, and all the remainder of the input we have seen so far, it is passed as past key values. Okay, and attention mask, we add one over here, and then we generate it. Okay, so by reusing key value pairs of the prompts or the tokens we have seen so far, we can reduce great amount of time. Okay, now even though it is fast, but it's not that it doesn't come over without it has its own shortcomings, right? So let's say that we are using float 16 numbers, right? We have 12 layers, we have like some dimensions, right? So what happens is KV caches grow very rapidly with the sequence length. Okay, so let's say that we have a sequence length of 1024, sequence length of 1024 or 512. Okay, and we have batch size of 12. So KV cache grow very rapidly for long sequences. Okay, how does this formula comes into picture is 2 is because for each token we have key and value numbers. Okay, so hence 2. Precision is basically if the precision is 2, right? So if you are using float 16, then we have 2 bytes. So 2 is our precision. Okay, 2 bytes over here. Then we have number of layers stacked up in a transformer. Okay, so as many number of layers we have, as many attention blocks we'll have, and as many attention blocks we have, we'll have to store key value pairs corresponding to each token per attention block. Okay, this is a dimension, like how many bytes, how many numbers are used to represent one token. Okay, and this is how the number total we get. Okay, we'll see later down the line like what these numbers look like for actual models. Okay, how fast KV caching have memory overhead. Okay, so is there any doubt so far? Hello.
Yeah, I have asked a doubt, but you can take that at the end, huh, Ankush? There is one doubt I
Sure.
posted in the chat, but no doubt. You can take it.
Sure. Let's take questions at the end. Okay. Yeah. So this is about KV caching. Next thing is batching. So as you have seen, we have calculated this. We are calculating this sequentially, right? For we are passing this texts one at a time to our model. Okay. Now that's a very inefficient way to do. And how do we get rid of that inefficiency? By batching. Okay, so batching is very effective and it speeds up the process. How does it speeds up the process? Let's discuss that. Let's say we are working on a GPU. Okay, now a pre-fill stage, okay, is when we work with GPU. One thing to remember is that most of our time doesn't go into computing because GPU is very fast at computations. Our bottleneck there is how fast we can take some data from CPU to GPU. Okay, that's the bottleneck. Now, when we take text one by one to GPU, that's we lose a lot of time over there, right? If we can just pack it up in one batch and send it, then we don't have too many memory trips from CPU to GPU. So that's how batching helps when we have GPUs. Now, when we don't have GPUs, still we are able to achieve some speed up. And why is that? Because in CPUs, like our frameworks are optimized in such a way that they get benefits of vectorization and optimized matrix operation using libraries like cuBLAS and which are like lower level code embedded in let's say Python or PyTorch. Okay, so that's how batching works. Now, with batching comes some level of bookkeeping. Okay, now when we pass text to model one at a time, then what we are giving is one sequence. Okay, that sequence has a length, it has a start, it has an end, and model it is clear to model that uh, what are the positions of the tokens in that single sequence. Okay, now when we batch number of texts into one entity, right, then it may not be necessary that all of them will have same length. Okay, but when we do batching, we are dealing with matrix multiplication, right? And we can't have a matrix in which one row is like three words, three long, right? Another row is four long, right? They have to be uniform. So that thing is solved via padding. So what happens in padding is uh, we pick the longest input in the batch, and then pad other sequences according to that. Okay, so that's what padding is about. We'll see it in action code just next. Another thing is position ID. Okay, so as we know that when we generate text via transformers, there is this thing called positional embedding, where uh, some number is added to the text embedding, token embedding, based on the position. Okay, now, when we pass a single sequence, it is very clear to the model that first token has zero position, second token has one position, and all, right? But when we do batching, then because of padding, we need to explicitly tell that what is the position ID of each token in each sequence of that batch. Okay, so that is something that we have to tell explicitly, and that will have to put it up also. So basically, here in this code, we are telling the tokenizer that we are going to use this as our pad token, which has value 50256. And we are also telling model that this is our pad token. Okay. Then we are also telling tokenizer from which side to add padding. Okay. It makes sense to add padding on the left side because generation happen on the right side, and our model has learned to process non-pad tokens to generate the next, right? So we can't have pad tokens on the right side. So it makes sense to have padding tokens on the left. So that's what we are telling the tokenizer here. Now, let's say we run this code, right? So this is a sequence, and this one is the longest. Okay, so we'll see that in our batch, it is reflected that this doesn't have any pad token. Okay, it has one pad token, it has two pad token. Likewise, this has three pad tokens. Okay, and same thing is reflected in attention mask also. So what attention mask tells model is that you ignore the input which has zero values, right? So likewise, that's how model is able to ignore the pad tokens and start working from the actual tokens. Okay, so now let's generate this thing with batching. Okay, so I'll run this code first, and then we can discuss in detail what is happening. So when batching, same 12 examples took 1.3 seconds, which is in comparison to I think 4 seconds when we used KV caching. So now this is like batching also as well as KV caching. So that's how batching helps us reduce the time. Okay. So now in batching, what we need to take into consideration is that we are passing, instead of one text, we are passing all the text at once. Okay. So instead of a vector, now we are getting a matrix, just to oversimplify. Okay. So next input is like a matrix where each row correspond to the numbers corresponding to that particular text. Okay. Now what we have is, now since we are using batch, then we will have to explicitly provide position IDs. Now attention mask is automatically governed by tokenizer, and it makes it accordingly, right? As we have seen over here, that attention mask is already as per pack tokens. Now what we do is, this code adjusts the position IDs according to the attention mask. Okay. So now what will happen is, by default model would have considered this token's position ID 0, this 1, 2, 3, right? But when we explicitly do it, then model will have to like, we are giving this token's position ID as 0, okay, and ignore the previous tokens. So this keeps our generation mostly sorted. And once we have done that, when we do next inputs, what we are doing here is, what was like addition of one next token ID, we are adding the entire batch, like a vector of next token IDs to existing input IDs. Okay, so this is our vector over here. Position IDs, what we are doing is just adding one to the entire vector. So previously, what we were doing is, we were wherever we are dealing with a number, now we have vector. Okay, and wherever we had a vector, now we have a matrix. So that's how, by explicitly setting position IDs and attention mask, we are able to make matching work. And as you can see over here, it takes a lot less time. Now think of it from the perspective of a running server. How does batching happens there, right? So one request is coming now, another can come sometime later, or let's say 10 requests comes at a time, right? How do we deal with that scenario? How do we make best possible use of our hardware in those scenarios? So in comes continuous batching. So what happens in continuous batching is, in normal batching, what we do is, we create a batch, let's say of here we created a batch of 12, right? We created a batch of 12, we waited for this batch to finish, and then we created another batch. Okay. Now we can do better than that. And how do we do that? By continuous batching. So instead of waiting for the batch to finish, what we can do is, at each token generation, we can ask ourselves, is there any request in a batch complete? Can we remove it and place another request over there? Okay. So here we have three functions. One is filter batch, another is pre-fill batch, and another is merge batches. Okay. Let's talk about them one by one. Pre-fill batch is basically, what it does is, whatever batch we have, right, it tokenizes and prepares input for that. Okay, that's what pre-fill batch does. Filter batch, what it does is, at each point it checks whether there are some texts which are complete, so it can be removed out of the batch. Okay, and once some requests are removed from the batch, uh, there is some space in batch. Okay, and now what we do is, we bring some more requests from request queue, and we fill those remaining slots in the batch which were recently emptied by filter. So when this happens, this is a long code. Let me. I'm sorry, I'm rushing a bit, but I'll share this notebook with you, and you can later on look. But here, key things to remember is basically that when we do this. So let me run it. Okay, so basically this is our batch. Okay, and as you can see over here, there are some statements like some text which needs to generate more, and there are some which needs to generate only 15 tokens. Now, although this came first, what will happen is the shorter statements which require less tokens to be generated will get finished first, and then later on this will get finished. So what happens over here is uh, the first thing that got out was big brown fox jumped, right? So 15 tokens it got out. Okay, then Humpty Dumpty 30 tokens got out. More such requests went into. Okay, Jack and Jill went into, but the longer requests are getting generated last. Okay, so we see Jack and Jill over here, Jack and Jill over here. They are taking their own time. Meanwhile, the shorter requests are getting generated, moved out of the batch. Newer requests are being accommodated, and that's how it goes on, right? So this is what continuous batching does. Okay, so with the help of continuous batching, we kind of free user to choose, how they batch it. Okay, while also maximizing our hardware utility. Okay, so this is a way how we can keep our hardware as busy as possible, just by filling the batch whenever it is possible, removing out the request that has been already processed. uh, so that's how continuous batching works. Okay, so that was about continuous batching. Now let's briefly talk about quantization and adapter based fine tuning. These topics are little they deserve a talk of its own, but we'll try to cover briefly and how they help someone who is interested in serving LLMs. Okay. So as we can see over here, uh, one way is quantization. So we already saw the GPU requirement that all the models are taking. Okay, in the beginning of this talk. Okay, so what quantization does is, let's say we have a 7B model. Okay, and it is being represented in float 16 representation. Okay, now what we can do is we can just round off all the parameters to a lesser precision, let's say int 8, and reduce the size, reduce the memory requirement by half. Okay, so that's how quantization works. So before we talk about quantization in detail, let's talk about the floating point representation. So there are like different floating point representation: FP32, FP16, FP8, and they are defined by how much bits. So 32 bits is used by FP32, and we have mantissa part and exponent part. Okay, and they define what is the range of the number that we can represent. Uh, 1 byte can represent. Okay, and how precise those numbers can be. Okay, so likewise, when we move to FP8, there are only 2 bits in mantissa and 5 bits in exponent. Okay, okay, there is something. I think it's 3. Okay, so no, not 3. One is sign bit. Yeah. So as you can see, when we move from one precision to another, the value that we are able to represent by that notation changes. Okay, FP32 is most precise, but they take more memory. FP16 takes half the memory, but we lose some precision with which we represent those numbers. And FP8 just use 8 bits, and we just lose a lot of precision when we dumb down our representation to FP8. Okay, so how does quantization helps? So number one is basically it also eases us on our cache KV cache requirement. Okay, let's say we are dealing with Llama 270B model of sequence length 1024. Okay, and this is our batch size. So if we are having a batch size of 64, then it takes 20 GB of KV cache. Okay, in FP16. When we move to int 8, that requirement is entirely halved. Why? Because all our parameters, model parameters, are now being represented by half the memory that they were taking earlier. So that is one advantage of quantization. But quantization should be used with caution, because uh, when we reduce the precision of the parameters, it sometimes behave in weird ways. Okay. So now what we'll do is we'll go through a short example where we'll quantize this GPT model and compare the generation of it. Okay. So we already have our model, and we just check. So currently it's 486 MB model. Okay. We define a function generate, where we can tell it how much token it has to generate. We pass the model in tokenizer and we generate. Okay. So our existing model, uh, it generates this, right? So quick brown fox jumped on its hind foot and it moved forward, moving towards Ruby fluid eyes, right? So this is what it is generating. Now what we'll do is we'll quantize it, again dequantize it, and then generate text based on the dequantized model. Okay. So this is our function that takes a tensor and generate the quantized version of the tensor, and we also have state, which helps us retrieve the same tensor again. Okay, recover the same tensor again when we want to. Okay, we have dequantize function, which uses a state as well as the quantized tensor, and try to regenerate the same tensor from which it was quantized. Okay, how do we do that? Look at it this way, that let's say we have it, we'll run it. So let's check it. So here, what we do is we take a random 2 cross 3 tensor. Okay, so we have 6 numbers. This is our original tensor. Okay, and these are the numbers how it generates. Now, when we quantize it, what it does is it moves all these numbers to the value between 0 and 255. Okay, and along with that, we get a state. State tells us what is the minimum number and what is the range. And by using these three, we can actually recover the same tensor back. So that's what we did here. And as you can see over here, when we recover the same tensor by quantizing and then dequantizing again, we don't get the exact numbers back. So 1279 is 1246. 1236 is like 1211, right? So it's a lossy translation, and that's why we should use this thing as with caution. Now, let's. This is about quantizing and dequantizing a tensor. Now we do the same thing with the model itself. Okay. So what we do is all the model named parameters, we pick the tensors and then quantize it. Okay. And then we, for dequantizing, we apply the same dequantize function to all the tensors. Okay. To all the model parameters. So when we do this, okay, our dequantized model basically is reduced to 130 MB. Why? Because we have moved all the high precision to low precision, and we are using just 2 numbers per tensor to retrieve that, to recover that same tensor again. Okay, so hence we are able to reduce it to, let's say, from 470 to 130 MB. Now what we'll do is we'll again dequantize that model using states and the quantized model and see how generation happens. Okay. So quick brown fox jumped on top of them but missed after landing. He ran away crying to his puppy. You know, and then lying naked, naked, naked. You know, this is something happening, right? So we see some degradation over here when we quantize a model, then again recovered it, right? So ideally, in an ideal world, recovered should work same as the original model, right? But that doesn't happen because that translation is lossy. Now there is one question, like whether whether we should use dequantized version of larger models or we should use whether we should use quantized version of larger models, or we should use full precision smaller models. Okay, so there has been a study by Meta, and what they suggest is that you are better off using the quantized version of larger models than the full precision smaller models. Okay, so I'll have that link. I'll share that link with you, and you can dig in deeper into this. Okay, so this is how quantization works. This is very primitive example that we used. There are a lot of recent developments that had happened in quantization. uh, One of them is quantized aware pre-training, which where you train the model taking into consideration the quantization aspect, and it works a lot better than just plain quantization training. So yeah, this is about quantization. Next thing we are going to talk about is adapter based fine tuning. Okay, so initially when we used to fine tune models, okay, it was, so what happens in fine tuning is basically you continue the training of the model, okay, for a specific task. Now it can be an instruction fine tuning, or it can be teaching your model to work well for your documents, for your data. Okay, so initially what used to happen is that we used to fine tune the entire model, and entire model weights were updated. Okay, and later on what was observed is that very small fraction of all the parameters used to get updated during fine tuning. Okay, so then what did is people exploited this fact, okay, and started representing that change matrix in lesser memory. Okay, how did they do that? Is instead of fine tuning the entire model, what they did was they fixed the pre-trained base model, okay, and represented the change matrix as two matrix. Okay, so let's say I have a 100 cross 100 matrix over here. Okay, now what I can do is I can do 100 cross 10, 10 cross 100 over here. Now when I multiply 100 cross 10 by a 10 cross 100 matrix, I again get back 100 into 100 matrix. Okay, but overall number of values that I have in those two matrix are lot less. They are not 100 cross 100. They are 2 into 100 cross 10. Okay, so they are lot less. So what happens is we are able to fine tune our model in this way with lot less memory requirement. Okay, and while inferencing, what happens is we just add these to this, and we are able to infer. Okay, so via these type of fine tunings, it's called low rank adaptation. Why low rank? Because it was observed that the change matrix is low in rank. It is very sparse, and it can be represented in a lesser rank decomposed form. Okay, so how does it help in inferencing? That we'll discuss next. So let's say that I have a small base model. Let's say Mr. 7B. Okay, and I train it, fine tune it for different tasks. Okay, now if I didn't use any adapters or adapter based fine tuning, what will I'll have to do is I'll have to keep three base model versions on my machine. Okay, so and that is very expensive. Now, what I can do with adapter based fine tuning is I can keep just one base model, and I can keep the adapter weights for all the three different use cases for which I fine tuned. Now, based on the input that I'm getting, I can plug these different adapters and serve my users. So there is like nearly equal to one third of reduction in my memory requirements just by using different adapters. Okay. Now there are different progress that has been made in this also. We have QLoRa, which combines quantization as well as low rank adapter fine tuning, and make use of that. So definitely we can have another talk to discuss that thing in details. Uh, if you are interested this topic, there are some good courses on deep learning AI. Please go through it. This talk was inspired from that only, and I've attached some references also here. Please feel free to go to it.